Good afternoon, everybody. Welcome to the Contribute and Collaborate track. We have a packed lineup of amazing talks this afternoon. So this is the cloud native. I understand not all the projects in the room are part of the CNCF. Most of them are. So we'll start with Paris right here. She will talk about the Kubernetes contributor experience. Then we'll move on to CSI, Saad Ali right here. We'll talk about the container storage interface. Then third talk is by Dan Berg and Zach Butcher from IBM and Google talking about Istio. We have Yuri Shukuro from Uber talking about Jaeger. Eduardo Silva from FluentD. And finally, Priyanka from Lightstep talking about open tracing over there. So the way this is going to work, we have 7 lightning talks of 10 minutes, which will go for the first hour, also a little bit over for the first hour. And then we'll break into groups for an hour of birds of a feather discussions. So we have open tracing and Jaeger, Istio on that side, Kubernetes contributor experience in the back over there, Spiffy over there, CSI and FluentD. And I realized I just forgot Spiffy. I'm so sorry. So we have, did I say that right, Spiffy? Spiffy, Sabri is going to talk about Spiffy. So that's really good content. So the questions, keep them for the bird of a feather. So we won't be taking questions. So speakers won't be taking questions when at the end of their talks. So good to go. We're good?
This laptop's good to go.
Okay, great.
All right, great. Hi, everybody. I'm Paris Pittman. I work at Google. I am going to literally run through the next 10 minutes with tons of info. But luckily, I come stacked with a ton of Kubernetes contributors. They're all in the round table over there, sitting in the back. First, some of the data points that I'm going to hit today are going to be around the community and show you where we get that data from. I'm going to tell you a little bit about the composition of the project, how decisions are made, and the communication platforms where we talk, and we being contributors. And then also I'm going to hit on some common entry points, and then we can discuss further at the table for any specific questions. So how do we measure this community? The CNCF and contributor experience members that I'm a part of have created this dashboard. The links are actually at the top of all of my slides, so when I upload the slides, please feel free to click on any of the links. But that is actually the live URL if anybody's interested in looking as we talk. But these are some really cool stats. For instance, we have 20,000 contributors across 107 repos that we watch that are a part of our ecosystem. So as you can see, it is a large community. It's also important to note that the definition of contributor here is wide and vast. We consider contributors those who are filing issues as well as making comments, not necessarily just committers. We have 427 contributing companies as of last quarter, which is awesome, which shows our vast ecosystem and many, many companies who are interested in donating their time and resources to Kubernetes. And then 1.1 million contributions to date. And again, contributions in this case would mean comments and issues and things along those lines. And then you can see the difference there with the commits to date being almost 100K. So the composition of the project and the way that we divide the work is through SIGs, working groups, and subprojects. Those are a lot. I think we've got 41 at this point with SIGs and working groups. What's a SIG? So a SIG is a special interest group, people who have come together from many companies, including their own independent selves, and they take on certain topics, for instance, networking topics. These SIGs can be project-based, They can be horizontal or they can be vertical. Vertical means that they're in a very specific niche, like networking, or they could be horizontal, which is like architecture, SIG architecture, that makes the technical decisions for the project as a whole. And then, of course, project, which is contributor experience, the SIG that I co-chair. And we're specifically interested in how you as a contributor are liking your experience and making sure that your workflow and things like that are complete. So SIG's YAML is actually how we power the READMEs and subprojects, which I'll get into in a second, for display. You can take a look at that. Of course, it's a YAML file with Kubernetes. The SIG list is on there as well. Also, you can find all of this documentation that I'm referring to inside of the Kubernetes community repository. So if you're following along, feel free to dig in there. Also, good news on that front, we are creating a contributor website that's going to boil up all of these documentation, all of these parts of the documentation that people are digging through our repos trying to find. So that's going to be awesome, and look out for that, I'd say, within the next 90 days. So subprojects I mentioned before, that is really where the work gets done from a technical decision-making perspective. So if you're poking around the repositories and you have no idea about code ownership or who makes technical decisions, this is where you would find out that information. Subprojects are listed on the READMEs of each SIG. So if you go into the community repo and pull up my SIG, for instance, you'll see this little excerpt. For instance, community management. This is tied to the code/doc base that we own, and that's how the project divides that work. And then owners files. So owners files are attached to the subprojects, and those owners files are have the reviewers and the approvers listed for your PR process, as well as certain automation. Automation being Prowl. Prowl is what we use to do automation in regards to assigning labels like LGTM when something looks good. So if there is not an LGTM label on something, the bot will come up and says that it's missing a label in order to merge. But the owners file is really helping us out with that kind of automation as it relates to who gets what for reviewing that PR or approving that PR. And if you're a new contributor, I think this is the best place for you to look if you're filing PRs to see who exactly you should assign things to, if there's not already somebody assigned to that. And in order to get those privileges in the owner's file, in order to be a reviewer, in order to be an approver and things like that in the community, we have a community membership doc. This really describes the roles and responsibilities of those individuals and how you can actually get there. So for instance, the first rung on the ladder is member. And that is a few PRs, and you've built a trust of people, and that you have sponsors, and that would grant you membership. In order to be assigned issues, at the very least, you have to be a member of the Kubernetes organization. So that's something you should check out if you're interested in a long-term contributing path with Kubernetes. And how we talk to each other. This is probably critiqued all of the time because we have a lot of communication channels, but each one of these actually serves a very good purpose, and I'm going to go through them very quickly because there are a lot. First things first, Slack. Slack is where we have 35,000 people talk, 6,000 active on a weekly basis with 160 channels. So it's a very, very active Slack. It's good for daily kind of conversations that you're having, not necessarily decision making or design proposal making or anything like that. If you want to think about it as like the aim of the water cooler, if you will. But that's really where new contributors can get a lot of really good information on the Kubernetes-dev channel, as well as all the SIGs have their own channels. So if you want to introduce yourself to people, that's a great resource. The mailing list, that's where a lot of our decisions do get made outside of GitHub. So if you're interested in contributing, please join some of the SIG mailing lists that we have. We also have a steering committee mailing list that you can join and see what's going on with the steering committee. And the steering committee is our governing committee of mostly founders and people who were elected into this just recently. And they do guidance as far as governance. And then K users and K dev, that would be Kubernetes users and Kubernetes dev. I just abbreviated that. And then we just put up something for discuss.kubernetes.io, and this is actually taking off with our users. So for contributing purposes, we probably won't have too much, at least for the time being, possibly subject to change, but our users seem to be flocking to this as it's not a walled garden like Slack, and it's very searchable, and it's cool because you can see people asking for tips and tricks where the docs don't have a purpose and serve a purpose there. Of course, GitHub is where all of our decisions are made via pull requests, issues, and comments. And then, of course, we also have SIG and working group weekly meetings. And the SIG list will actually tell you where you can go for those things. Mostly Slack will have the information inside of each special interest group. But you can also see in the bubble, too, we have tons more communication platforms. But as far as main where you can go to get contributing information, the ones that you see outside of the bubble are your best bet. So quickly, common entry points for new contributors. So if you are interested out there right now in making a PR, first sign the CLA. That's, before we go any further, pretty much a requirement. So I would just go ahead and make a point to do that now. And then the first is to join some SIGs and working groups, mailing lists, Slack channels, et cetera, that either personally interest you or professionally interest you. So if you are big on IPv6, I always give networking as an example, but if you're big on IPv6, you should probably join the networking SIG, because those are some of the issues that they work on. Or if storage is your thing, you work for a storage vendor, then maybe check out the storage SIG. But just be a fly on the wall. I know I've only been with the project for about 9 months now. So it's very important to just kind of take in how that community works, and then ultimately see what value you can add to that crew. They often ask for new contributors to step up during their meetings, and that's a good chance for you to introduce yourself. You can also ask for help wanted and good issue first time labels and things like that at the meetings, and let people know of your interest, especially if you're on it full time or if it's just a hobby. Or join a project SIG, and a project SIG is, again, a special interest group that's concerned with the majority of the project, not necessarily a niche. And things like the release team, contributor experience, docs, those are huge entry points for even code contributors, because you get a feel for the entire project with those groups, especially the release team. We actually have some previous release and actually current release leads with us, so they can tell you about their experience with the release team. And then with contributor experience, we had one contributor recently come to us and say that our guide sucked. And I said, PR's welcome, and now we have a new guide. So that was a perfect story to a open source love story. And then speaking of new contributors, we actually just ran a new contributor workshop at our last contributor summit, and it went smashingly well. So well that we did a video on it, and yes, you can watch the video. It's 3 hours long, but we did chunk the video down, and there is actually a snip of the outline that we have. So if you're just very concerned with certain pieces to the contributing pie, please go ahead and look at that. And then also, since I only had a few minutes here, and I really breezed through most of that information, so I apologize. There's 2 talks that you should definitely watch from KubeCon EU if you are very interested in contributing. One is The Machines Can Do All the Work, Automation in the Kubernetes Experience, Automation and the Kubernetes Contributor Experience by Aaron Krickenberger, who heads up the testing special interest group. They've done significant work on labeling, which is a key part to our story. And you can see that's how we manage all of the issues that we do. And then, of course, growing in your contributor role, Tim Pepper, and he offers so many different entry points than what I did in his talk. So please watch those things. And then last but not least, my info, and I'm just going to keep this up for you for a second. If you have any questions, see me in the back. Cool? Thanks.
All right, can everyone hear me okay? All right, great. My name is Saad Ali. I'm a software engineer at Google, and I work primarily on storage for Kubernetes. Over the past year or so, one of the main projects that we've been working on for Kubernetes is the container storage interface. So with the container storage interface, I wanted to tell you about it today, where it came from, what it is. I've only got about 10 minutes or so I'm going to breeze through this very quickly. If you have any more questions, you'll find me at the table afterwards. So first of all, what's the problem that the container storage interface is trying to solve? At a very high level, a container orchestration system takes a bunch of containerized workloads and distributes them onto node machines that are available. That could be, you could have 20, 30, 50, 100, 1,000 machines. Wherever your workload lands, ideally you want your storage to be available there as well. If you are familiar with Docker volumes, for the most part, they worry about making a particular type of volume available to a container on a specific machine. At the Kubernetes layer, we want to make volumes available to containers wherever they're scheduled, no matter what machine they land on. For the most part, we've done a pretty good job with this, and the Kubernetes volume layer is pretty robust and has a lot of cool technologies like dynamic volume provisioning. That allows a volume to automatically be created when storage is needed by a workload. But the problem with what we have in Kubernetes is that all the volume plugins that we have are basically in tree. What this means is that the NFS plugin, the iSCSI plugin, GCEPD, AWS, all the code for those plugins is actually written into the core Kubernetes code. And it's compiled and built and shipped with every binary that's shipped with Kubernetes. This is great when we first started the project because it allowed us to iterate very quickly. But it's starting to become very painful because adding a new volume plugin means that you actually have to go and check code into the Kubernetes repo. You have to align with our release cycles. Bug fixes means you have to align yourself with this massive project, which can get pretty painful. And it's not just painful for storage vendors who are trying to add code to Kubernetes. It's also painful for us as Kubernetes developers because we're trying to maintain code that we haven't written, and we really have no way to actually test. So ideally what we want to do is have some sort of pluggable system that will allow volume plugins to be written outside of Kubernetes, but still retain the full power of the Kubernetes volume subsystem. Now what we realized when we first started to tackle this issue about a year ago was that we weren't alone in hitting this issue. We talked to folks from Docker, Mesos, Cloud Foundry, and what we realized was that basically all the cluster orchestration systems were hitting the same set of problems. And there were storage vendors that were also trying to come up with frameworks that would hook into Mesos, Docker, Cloud Foundry, and Kubernetes. So everybody wanted to solve the same set of problems. We could have gone at it alone with Kubernetes, but what we decided was let's come up with a community standard that everybody can get behind. And so we kicked off the CSI project in the hopes to define an industry standard for container orchestration system volume plugins. So really quickly, what is CSI? CSI is basically 3 main use cases. One is creating and deleting a volume. Second is attaching and detaching a volume. This basically means that if your workload is scheduled to some arbitrary machine, make sure that that volume is available on that machine. And then the third is mounting and unmounting a volume. That means actually making it available inside the container that needs it. So at its core, it's very simple. CSI continues to evolve. We just shipped 0.3 a couple of weeks ago, and that added support for snapshotting, for example. And we're open source. We're hosted on GitHub, and we're always welcoming volunteers and contributors. Anybody who's interested in this space, please come join our community. I'll talk a little bit more about that in a little bit. While defining CSI, it's also important to note what CSI is not. CSI is a specification. It's an interface that we define. A storage vendor can implement that interface. A CO can implement integration with that interface. But CSI itself doesn't define what the packaging of a CSI driver should look like. It doesn't specify what monitoring, what the deployment of that plugin will look like. So we leave that up to the vendors, the storage vendors to decide, and the COs to decide. We don't define grades of storage. So if you're familiar with, in Kubernetes, the concept of storage classes, we haven't codified that into the CSI spec because we believe that you can actually enable the idea of a storage catalog using the primitives that CSI exposes. So next up, I'm going to talk a little bit more about what the CSI spec actually looks like. It's a gRPC interface, and it's segmented into three main services. The services are called controller, node, and identity. Identity is pretty simple. It's basically just a set of calls that allows you to get information about a particular plugin. What is the name of the plugin, that kind of thing. Controller is a set of calls which can be executed from anywhere on the cluster. So for example, if you want to provision a volume, ideally that call can be fulfilled from anywhere on the cluster. And node is the set of calls that can only be fulfilled on the machine that the workload is scheduled to. So if you're thinking about storage and actually mounting a particular volume into a container, ultimately the code that is making that happen has to be executed on the machine that the workload is scheduled to. So the idea here, by segmenting it into node and controller, is that the cluster orchestrator will guarantee that the calls that are in the node service are going to be executed on the node that the workload is actually scheduled to, whereas the controller calls may be executed anywhere on the cluster. And now let's talk about naming. So I talked about these three simple steps: creating a volume, deleting a volume, attaching, detaching, mounting, unmounting. If you look at the CSI spec, the actual names are a little bit more complicated. Controller publish volume instead of attach. And the idea here was that these steps are not just attaching a volume, you could potentially be doing other things. So for example, instead of just mounting a volume, you may want to format that volume before you make it available. So just to be kind of more open and flexible, we wanted to have more generic names. So if you see these funny names, that's kind of what they mean. You can map that in your head. And at a very high level, these are all the methods that are exposed in the different services of Kubernetes. I've got 2 minutes left. I'm going to try to run through these very quickly. So if you look at each one of these services, they all have a get capability call. So there's controller get capability, node get capability, and plugin get capability. Basically what this is defining is the set of capabilities that a plugin has. Some plugins may not implement a control plane at all. So you could have a very simple, for example, NFS plugin that only knows how to mount and unmount NFS shares. It doesn't know how to create or delete shares, and it doesn't have a concept of attaching because NFS shares are equally available on all machines in the cluster. So all it would do is implement a node service, and the plugin capabilities would not advertise the controller service at all. And then similarly, within the controller service, you have controller get capabilities. It allows a plugin to say, I support the creation and deletion of volumes, or I don't. I support snapshotting, or I don't. So basically, it's a way for a plugin to advertise what it's capable of. And then create and delete volume on the controller service is fairly straightforward. It provisions a new volume and deletes an existing volume. Controller publish and controller unpublish is attach and detach. Make that volume available on a specific node. List volume is just give me all the volumes that exist on the system. Get capacity is give me the capacity that is available to provision new volumes. Validate volume capabilities is if somebody gives me a pre-provisioned volume, can the storage backend please verify that this is a valid volume? And then create snapshot, delete snapshot, list snapshot is just for creating snapshots, deleting snapshots, and listing snapshots. The node service are the set of calls that are going to be executed on a node machine. Node publish volume and unpublished volume is the equivalent of a mount or unmount. They could also do things like format a volume, and ultimately they're responsible for making a volume available at a specific path on the node machine, and then the cluster orchestration system like Kubernetes will make that available inside the container. Then you have node stage and node unstage. The difference between node publish and unpublish and stage and unstage is that stage and unstage are called once per node per volume, whereas publish and unpublish are called for every single workload. So the first workload that gets scheduled to some node will trigger the node stage, and then every subsequent workload that references the same volume, node stage is not going to be triggered for, only node publish will. And that is pretty much it. So node get ID is a way for the node to advertise what it believes the name of the node is. A storage system can have a different way to reference a node than the cluster orchestration system, and we wanted a way to be able to get that mapping. In the future, we're actually going to replace this with node get info because we realized that it's not just node name that we want. We also want topology information because a volume may not necessarily be equally available throughout a cluster, and we've introduced this. We're introducing this concept of topology that allows a cluster orchestration system or a plugin to advertise to a cluster orchestration system where the volume is going to be available within the cluster so that the CO can make smarter scheduling decisions based on that information. So current status of CSI. CSI was published as a spec in December as a 0.1 release. Since then, we've had 2 releases, the most recent one in June, which added support for snapshots, topology, and a couple other things. And then on the CO side, on the Kubernetes side, we started implementing it in 1.9 as alpha. We moved it in Q1 1.10 to beta. In the most recent release, 1.11, which is coming out at the end of this month, we leave it in beta but add support for block volumes. And we're going to hopefully drive towards GA by the end of the year. Mesos has also implemented CSI as experimental. Their 1.6 release is going to support 0.3. Cloud Foundry also has experimental support, and the folks at Docker have also been working very closely on the spec, but I don't believe they've started implementing it for Docker Swarm yet. Plugin implementation has also started. There is a GCE persistent disk plugin out there. There is a sample NFS iSCSI plugin. We have Luis over here from Portworx who has an awesome working plugin as well. So you can talk to us if you're interested in writing a driver. What's next? We're going to drive to 1.0. There's a lot of work that's left to be done both on the specification side as well as the implementation side. I'm out of time, so I'm not going to go into detail about that. So last thing is how to get involved. Actually, one thing I want to mention is CSI is actually not a CNCF project yet. CSI was a collaboration between Kubernetes, Mesos, Docker, and Cloud Foundry, and currently operates as an independent project. We plan to eventually be inducted into the CNCF, but just a minor note that we're not actually part of the CNCF yet. That said, we have community meetings every week. You can go to Kubernetes storage interface /community to find information about that. The discussions there are generic to the Kubernetes spec. They apply to all cluster orchestration systems. If you're interested in the Kubernetes side of things, we also have Kubernetes-specific CSI meetings with the details there if you're interested. I don't think I have time for any questions. I'm going to be in that corner, so feel free to grab me later. Thank you very much.
Hey, so I'm Zach. I used to be at Google. About a month now, I'm no longer at Google. But I was one of the early Istio contributors there and have moved on to a company now building on top of Istio. And so in the next 10 minutes, I'm going to give you kind of a whirlwind tour of what Istio is, what it tries to accomplish, and how it does that. So it's not really valuable for me to talk about it unless we know kind of what the problem that we're going into is. And so this really is the problem that defines Istio. And it is exactly as it's up on the screen, right? As we move to these modern distributed architectures, our tooling and the way that we're used to operating our deployments just doesn't address the problems that we have. So when I say a modern distributed architecture, I mean a couple different things here. I mean this move towards breaking apart monoliths into individual pieces, and businesses want to do this so they go faster. We tend to package those as containers. They get deployed into environments that change a lot. And probably most importantly from Istio's perspective, now the network is in the middle of our application. Whereas before we made procedure calls, now they're going over the network, and there's just a world of difference there between local calls and remote calls and how I, as a developer, try and diagnose problems in my system. All of the tooling is different, and frankly, today is not really where it needs to be to really enable developers. And so again, this shortage of tooling means we can't monitor, manage, or secure things. So what does Istio do? Istio monitors, manages, and secures things. That's the goal, at least. So Istio provides a platform to connect, manage, monitor, and secure. And when I say those things, what I mean is this. When we talk about connecting applications together, we talk about service discovery. How do I locate what I'm actually going to talk to? When I talk to it over the network, I want resiliency features because the network is flaky. And especially if I've taken this application that used to be together and I'm splitting it apart, now I need to handle things like retries, but even more than that, things like circuit breaking and lame ducking, so that my system becomes more self-healing. And load balancing, and ideally I don't want to pay for load balancing, right? I don't want to run these middle proxies in the middle and have two network hops to get everywhere, where I used to have one. I want to be able to do load balancing on the client side so that we can go directly to the target that we want to hit. When we talk about managing services, we mean a couple different things here, but primarily I want to manage traffic and how traffic flows to services and which versions of services it flows to, and we're talking about things like canarying releases, things of that nature. And also policy enforcement. So now I go from this monolith that had kind of one door in, and I knew very clearly how requests got to it, and I knew the things that it talked to. I now have this distributed system, and I have doors everywhere because all of my services are communicating with each other. How do I actually enforce things like authentication, who can talk to whom? How do I enforce rate limiting? I'm sure a lot of us have DDoSed internal services accidentally when I deploy a new thing. I do that. I've done that multiple times. So I want things like rate limiting as a policy that's interesting to me. And then we want to be able to monitor. We want visibility into what's actually happening. And this is maybe one of the single biggest pain points for developers today, is that I moved to this awesome architecture. I've containerized all my services, and they're deployed out now, and it's cool. And I have no idea where my problem is. We've had a customer using Istio, for example, that couldn't track down latency in their service graph, right? And you get this dependency graph that's like 20 services deep, and I can't figure out where the one is that's adding 5 seconds latency to my call. And so Istio can help you view that. And then finally, Istio helps you tackle security, and in particular, it tackles the problem of transport level encryption and provisioning identities that can be used there to do authentication and authorization of service-to-service communication. So how does it actually work? So this is our model application. It's about, it's over here. Here's our model application. It's about as simple as any application can be. We're just going to say A calls B. We don't really care how it does it, what the protocol is. It doesn't really matter. We just know that A wants to talk to B over the network. So the first thing that we do in this Istio deployment is we put a proxy on the same host side by side with the application, and we call this a sidecar deployment. And they actually exist in the same trust domain. So if we're in Kubernetes, we're actually deploying them into the same pod together. And importantly, they share a network namespace. Envoy is the proxy that we picked. It's an open source, by default. It's an open source project by Lyft. And one of the big reasons that we picked it is A, it was built for this kind of a sidecar model deployment, and B, it's highly configurable, right? It has APIs that I can push configuration to at runtime, and I don't have to restart my proxy to apply new configuration and that kind of thing. Actually, it's built to cope with these dynamic environments that we actually live in now. So then the second piece of Istio that we need to deploy to actually make things work is Pilot. And Pilot is really the service registry and topology piece. Pilot's responsible for talking to Kubernetes, for example, if we're running on Kubernetes, and getting information about the services and endpoints. If you're not running on Kubernetes, it's responsible for talking to things like Console or Eureka or Zookeeper, to try and understand the topology of the deployment so that we can push configuration to all the proxies so that they can route. And one thing I want to point out too is that this is actually a valid Istio deployment here. I can just run sidecars with a pilot to configure them, and I can take advantage of all the traffic management features that Istio provides without running anything else. One of the problems that we've had kind of historically talking about Istio is it's this big piece to bite off and run. But it's actually easy to run pieces of it. And so this is one example deployment of Istio that you can run if you are only interested in traffic management capability. So then we want to add in things like policy and telemetry. And Mixer is the piece that's responsible for both of those components of Istio. And you can actually pick either one or both. So I can say, I want telemetry about my deployment, and that's actually a pretty safe thing to do because that's not in our request path. Envoys in the mesh will process requests, and asynchronously they'll report back to Mixer, hey, here's this request that I had. Why don't you go generate metrics about it? On the other side, I can do things like policy. I can do things like authentication, authorization, rate limiting, all kinds of policy. We can apply at request time in the request path. And so these envoys will call Mixer and they say, hey, do I let this request through or not? And so Mixer can be on the request path there. And I do want to call out that it's only logically on the request path. Mixer doesn't actually get called one-to-one for every request through your service. All that information winds up being very highly cacheable. So we can still build an efficient system that can do cool policy, complicated policy verdicts efficiently across your deployment. And finally, we have Citadel, which used to be the Istio CA, and it's responsible for minting identities for workloads as they're deployed in a way that they can be proven. So in this case, Citadel will mint X509 certificates and give them to workloads. Those certificates encode the identity of the workload inside of it. And when services try to talk to each other, we can, we require mutual TLS, so we require that both sides have certificates that they can give us. And so we have both of these identities in hand, and that feeds back to things like telemetry. I can generate telemetry with this strong notion of identity that's attached to my metrics. I can do things like policy. I can write policy about which services can communicate with each other, and I know that the identities that those services give me, that policy is applied on, is strong, and I can go and verify that. So let's just walk through our call real quick. So if we have A wants to call B, what actually happens? So first off, no code changes in A. However, A was calling B before, you can do that. Typically, caveat is maybe some weird protocols or something like that. So A makes this call, and A's sidecar traps that request locally. On Kubernetes, that tends to happen with like an IP table rule, but that could be BPF or any number of ways that we could capture traffic. And Envoy client side gets the opportunity to decide where this request goes. So I look at the request and I say, hey, I know that A wants to talk to B. The sidecar, get to decide, or Istio gets to decide which instance of B and how do I communicate with it, where does it live. We get to do client-side load balancing, and a little bit of policy happens there. So we finally select a B that we're going to send it to, and we forward that request over. And the sidecar over on B side catches this request, and it says, hey, Mixer, do I let this request through or not? Give me a thumbs up, thumbs down verdict. Does it go through? We get a thumbs up, and again, that's highly cacheable, so even though that logically happens every request, in practice it doesn't. I'm out of time. B gets the request, everything goes back through the other way, and we report telemetry asynchronously afterwards. So here is the canonical architecture slide. And most importantly, come get involved. We just had our 0.8 release. 1.0 is coming out in hopefully the next month-ish or so, and that's really the emphasis there is on polish and refinement. And we're pretty happy with the feature set. We want to get into a shape that everybody can run it and feel safe and comfortable running it. So go hit us up on GitHub, go file issues, check out the website, and tweet at us. Cool. Thank you.
It's okay. It's okay? Yeah, I don't have notes, but this will work. Hi, everybody. I'm Sabri Blackman from Sitel. I'm going to be presenting very, very, very quickly about Spiffy, excuse me, and how it makes your lives easier centrally. So, because I don't have any notes, this is going to be very ad hoc. The problem, what's the problem that we're trying to solve here? Ultimately, Spiffy is trying to solve the problem about trust. And in this particular example, we have a source workload and destination workload. We're trying to send a message that could be an API call over some sort of protocol. Doesn't really matter. And the fundamental problem with identity and trust is how do we know the workload who's calling, the destination workload is who they say they are, and how do we know that they actually have the authorization to send that message in the first place? And so this is kind of a fairly accurate representation of what modern infrastructure looks like today. We have a large number of services. We have a large number of middleware, Cloud Foundry. You may have some things running on Kubernetes or OpenShift. You may have things running in multiple cloud providers. And so this identity problem or this trust problem becomes a lot more interesting as things become a little bit more heterogeneous. So there's been one of the traditional ways to solve this problem is sort of these protocol-specific ways of authorization or authentication. And so you can think of HTTPS authentication or logging on to a database. You provide some sort of username, credentials, password credentials, and yay, I've identified myself to that service. There are a couple problems with that. You have to figure out how an application actually gets those credentials in the first place. You also have to kind of figure out what happens if those credentials are compromised. How can I rotate those credentials? How can I revoke credentials in a way that's automated and easy? And then, of course, you're creating accounts on one particular system. That identity for, say, the web front end to the subscription is only valid for that one particular relationship. There's no way to associate those credentials with something else. So Model 2 is sort of a bit more of a modern example of how you could potentially do this. And you're leveraging information or security constructs from the underlying infrastructure. And so if you're using something like AWS, you can imagine that this is, AIM information that is provided through some sort of privileged API. If you're using Kubernetes secrets API, et cetera, which is a little bit better. But it still has the same problem of, well, what if your infrastructure itself is, across multiple platforms? Those identities are not portable. And so, not too long ago, Joe Beda, who super involved in Kubernetes and now with Heptio, kind of came up with this idea of the Spiffy specification. And the idea is that if you enable or if you implement the Spiffy specification, you can create and enable workload APIs that are portable across a variety of systems. and is usable basically universally. So spiffy, secure identity for everyone. And so some of the initial design goals of Spiffy was to be, extensible, so you can support a variety of different platforms. It needs to be API driven and policy driven, so we want to be able to automate. You want to be able to revoke identities and things like that programmatically. It needs to be highly available. And it really does need to be able to support some of the patterns of modern infrastructure today. So it has to support, workloads that are coming up and down many times a second. It has to be able to support, environments that are scaling up and down on a regular basis. And so those are some of the initial design goals. And so part of that spec, or the first part of the Spiffy spec, is the Spiffy ID. And so this really is a very simple way to establish an identity per workload. So 2 parts, very, very simple URI format using the Spiffy type. The first part of that is the trust domain. The trust domain defines a particular domain of trust, right? And so if you are established, if you have an identity in a particular trust domain, you can create policy with other services within that one domain. Second part of that is the workload identifier, and that identifies your particular workload within that trust domain. There's no particular rules around the workload identifier itself. If you want to implement some sort of like hierarchical directory, esque sorts of things, you can do that on your own, but the Spiffy spec doesn't enforce any of those things. So the second part of the Spiffy spec is the SVID. Right now, the SVID is X509 cert, but we're also working on the JOT certification. If you're interested in that process, it's actually going on right now. But these are short-lived documents that are provided to your workload via the workload API, which we'll come to next. But essentially, once you have proven your identity, this document or this SVID is what you can use to present to other applications. Hey, I am who I say I am. I have proof, right? These are signed from a common CA. That is associated with your particular trust domain. And so not only can an application verify that you are who you say you are, but that you are, we are part of the same group. And so the third part of that is the workload API. And the workload API is a very, very simple API that you can implement. And essentially, it provides a standardized way for applications to pull their workload identity. And so, very, very simple sort of process. I present, some information. I want my ID. The workload API performs attestation, which essentially means use underlying information from the platform that the service is running on to prove or to figure out if the application is who it says it is. There's quite a few plugins that you can leverage to determine, you can write these different policies to determine, whether an application is, you can leverage things like, the Kubernetes pod IDs or different labels or UUIDs and things like that. You can get pretty complicated with how you actually perform that attestation. But the workload API then returns an SVID to your application that you can then begin using immediately. The workload API also sort of defines some rules about how to revoke and rotate those certificates as well. And so Spiffy spec it's just a spec, right? Spire is sort of the open source implementation of the Spiffy spec itself. It relies on an agent to perform, to implement the workload API. And so that agent is available on each one of your hosts. It has to be installed. And then again, it leverages host information to perform the attestation of the host itself and also of any workloads that are running, that are being brought up on that machine itself. And so Spire is under the Spiffy GitHub organization as well. They're maintained by the same people. So I have 1 minute left. Oh boy. Once you actually have the SVID, and this is really why we're super excited about Spiffy, that SVID can be presented to a variety of different services. It's not just for service mesh, it's not just for secrets or authorization, but it can also be used for sort of the secure introduction to other systems, which could be something like HashiCorp Vault. I think the demo for that is coming out very, very, very soon, so we're excited about that. Because it's just an X509 certificate or JOT, you can use things like Nginx and Envoy directly with that SVID, and it works out of the box. And we're also working on a demo with open tracing. And so being able to embed Spiffy IDs into tracing so you can sort of associate metrics and things like that in a way that's meaningful. And then Spiffy Workload API. Spire, again, there's a variety of different plugins to tie into upstream CAs, HSMs, TPM, so you can leverage hardware modules for particular security information and things like that. I am out of time, so I will go over these very, very quickly. What Spiffy is not, it is not authorization, it's identity. What you decide to do with that identity is really up to you. We may provide some demos and examples, but you can kind of leverage these identities in a number of ways. It is not transport level security, but like I said, you can also use these SVIDs to actually perform mutual TLS. Things we didn't talk about a whole lot, but I'll be here afterwards to answer any questions you may have. And I'll leave this up for a little bit, but this is how you can get involved. Spiffy, GitHub, it's pretty active. We also have a Slack where you can join a number of different special interest groups. We have those weekly. The JOT SIG right now is underway, and that's really, really, really important. We can definitely use some more input on that one. And then there's 2 YouTube videos that go over sort of Spiffy in actual usage in a demo format that are super, super helpful. And that's it. Cool. All right.
Everyone. All right. Hi, everyone. My name is Yuri Shkuro. I work at Uber, and I'm a tech lead for the tracing team at Uber. And we built Jaeger as a tracing system, which is part of the CNCF foundation. So I'll talk about that. I will give a quick demo, which is probably I'm the only one to get to actually demo something in these talks. So just before I do that, I wanted to kind of ask for a quick poll. How many people are familiar with distributed tracing in theory? What it like from 1, 2, 3, 4, like 10, 15 hands? That's good. And how many people have actually used distributed tracing systems in their work? Almost the same people, almost. Well, it was good. So at least half the people seem to have this as a new information. So when Zach was talking about Istio, and he said, okay, imagine you have a service architecture with like 20 services, right? Well, this is kind of Uber architecture with how many services. It's not actually all of them. And so what happens is that, and this is typical of big companies like Facebook and Google, and so anytime you use a, let's say, mobile app, browse your Twitter feed or Facebook or taking a ride at Uber, it seems all simple, but what happens is actually each request to the backend spreads out through like many microservices and many instances of them. And so when we try to understand what that architecture is actually doing, and especially if there's a problem somewhere, it's very hard to diagnose. This is again was like mentioned in the like microservices world, and monitoring becomes really hard. Traditional monitoring tools like metrics and logs, they only tell you like a story about a single node in this picture. We want to have a story about the whole transaction going through the architecture, and this number of transactions like billions a day. So if something breaks, we want to pinpoint where in the architecture it breaks. So, and that's what distributed tracing does. Just go quickly through just a very high level idea of what distributed tracing, how it works. So let's say we have an edge service and then the request comes in. And what we do with that is we associate a unique ID with that request. We can call it execution ID or trace ID. We store it in a context, which is like a virtual concept of a metadata attached to that request. And then as we make more calls through our architecture, we keep passing that context with it, and so the request ID is available at every step, and that allows us to do a lot of interesting things. Like especially in the tracing space, we can actually measure all the interactions. We can track causality of who called whom and when, what the results were, how much time it took for every step, and we can build like a time sequence diagram that's shown on the right side that can explain what's going on with our system. So. Now that, let me just jump into a demo. So the demo is, oh wow. All right, so the demo is going to be with a very simple application that we call Hot Rod. It's rides on demand. It's a very like a test application which pretends to be a ride-sharing company, right? So you have 4 customers, and then you can click on a button, you get like a car dispatched to you. You can see what the driver license or like a license plate number of that car, how long it took for our purposes for like statistical information. And we can see that like the latency of this request keeps climbing up. So now we want to investigate what's going on with this application. But before we do that, let's say I want to understand first what the architecture of that application, right? We haven't seen it, we don't know what. So, and that's what tracing immediately gives me without any sort of me doing anything or having to understand the read and documentation. So it shows you that this application that appeared simple, but it already has like 4 microservices plus 2 databases. Apparently, it shows how the calls were made. So again, because we were able to trace every single request here, we were able to build that service diagram or service dependency graph from the data. And then, so we saw that the request, let me see, all right. So there is like some recent traces that were executed, and if I pick one of them, we can see what, so like a typical view what data tracing systems provide, and the same time sequence diagram that I showed in the slide. And what's interesting here is that at the single glance, we can see that if we are trying to understand what the performance issue was, why the latency was climbing, right, we can see immediately who is responsible for that, right? So there's this MySQL, do you guys see? I can make it bigger. MySQL call, which was taking the majority of the time, right? And so if that happened in production, I know who to blame and where I should go and optimize this particular application. Specifically, if I want to actually get more information, well, what specifically in that MySQL thing, I can drill down and I can see, oh yeah, this was the SQL, like a query that was executing. Shouldn't be taking more than a second. And then even more, digging even more deeper, like I see that there's logs attached to this individual segment. And I say, oh, I'm waiting for a log behind for 4 transactions, right? So this already kind of allowed me to narrow down to an issue with that applications, and there is some resource context on some on the resource log that I need to go and figure out what's going on, right? And yeah, it's kind of very obvious from the view of the trace itself. You don't have to scan through logs and try to correlate information as you would have to do otherwise. Another thing that we can see here is that so there's this. Well, by the way, I haven't explained really, but this is on the left, we see the services and how they called, like the parent-child, basically relationships between the calls. On the horizontal, the time, and so we have, basically, we see that, okay, front-end service called the customer service, and this is how long each operation within each service took. And then, so if you go over here, we can see that the front-end call, service called the driver service. And then the driver service made this tons of calls to Redis. So another thing that we can immediately see on the trace is this staircase pattern, which means all the requests were executed one at a time. So again, if let's say we solved that MySQL problem, right, and it's fast now, but the next thing we will get stuck is on this one, because clearly we're doing something sequential where we potentially could be doing parallel. And so if you parallelize that, you can collapse it all into one vertical line. It's going to be much faster. And finally, just yet another pattern we can see here between front end and the root service. service is that, so we can see here that like these blue lines, so 3 at a time, and they all seem to be fired off concurrently, which is good, but then just 3, and then they repeat, and then, so if we like look closer, like we can actually zoom into this. If we look closer, we can see that as soon as one of them, like this one, stops, the other one starts, right? So another indication of resource contention when you can only do 3 things at a time. If we actually fix the first 2 problems with MySQL and the staircase, then we would run into this where if I run multiple requests, not only this is going to be like 3 at a time, you can actually get 1 and nothing at a time, right? So because the actual resource contention is 3 for the whole application, for the whole service. And so as it executes more requests, they will start blocking and basically waiting. So again, we can find it simply by looking at the trace. I don't have to do any more investigation. So this is pretty much, I think, all that I can do as far as the demo in this quick thing, but just like a couple more points here that, so we can see this red signs, exclamation points, so they indicate errors that happen in the path of the request, which is also very useful. We can drill down and we can see what's actually exactly happened. So the log tells us, oh, this is the Redis timeout. So apparently it didn't screw up the actual application, which is good at resilient to errors, but we could go and investigate what's going on here. So what I'm really, if I go back to the slides, what I'm really demonstrating here is, all right, here it is. Yes, so let me present back. So the distributed tracing systems, and Jaeger is one example of them, they do several things. So one of them is we can clearly see we can actually go and troubleshoot distributed transactions in a very complex architecture, right? Another thing we can do is we can root cause analysis. When something bad happened in that transaction, we can quickly drill down and try to understand, which is very hard to do if you try to do the same thing with metrics or logs. We can perform, obviously, latency optimizations or other performance optimizations that we can find bottlenecks in the applications. And we've seen at the beginning we can do like understand what our architecture looks like, because when the architecture is as complex as I showed in the Uber, sometimes people don't even know, okay, I'm making a request from A to B, but what does B depend really? Maybe it actually is like doing fan out 200 more services. And we've seen situations in production where you open an Uber app, it really shouldn't do much to just open it, but when we looked at the traces, we saw that, oh, it was making a call to some credit card storage system. Like, why would you want to do that for opening an app, right? So this is like something creeped in it because of the complexity of the code, no one noticed it, and then, and it was causing performance issues, which was super hard to diagnose. But the tracing kind of displayed it based purely just on the dependency, on the service dependency diagram. And finally, the thing that I didn't touch about, but the context propagation thing that I mentioned, what the whole tracing is based on, it's actually a super powerful technique by itself. You don't have to do tracing with it. You can do other stuff with it. You can like partition metrics based on the context that you propagate. Like you mentioned with the SPIFFE, you can pass the identity of the call. You can actually pass the whole call chain in the baggage and partition metrics. It gives a super interesting results. So back to Jaeger. So Jaeger is a distributed tracing system that we created at Uber. We donated it to CNCF last year. It features open tracing support. Priyanka will talk about what open tracing is. It's like a general API for distributed tracing. And the reason why we sort of are behind open tracing API is because if you're a library developer or even an application developer, when you're making the decision how you instrument your application, you don't want to be tied to a particular tracing system and make a vendor choice at that point, right? And so Jaeger doesn't force you to do that. You instrument with open tracing. If you like Jaeger, you can continue using it. If you don't, you can go and like pick another vendor, and you don't have to rewrite all the instrumentation, which is arguably the most expensive part of distributed tracing. So backend is implemented in Go. Supports multiple storage backends like Cassandra, Elasticsearch is the two popular ones, and there are people working on other stuff. If you've heard of or used Zipkin, Jaeger can be used as a drop-in replacement. We support their inbound trace format, so you could like keep your Zipkin instrumentation and just replace the backend with Jaeger. We have actually a lot more features on the backend than Zipkin. if you want to get in touch, so I mean, let's say you have a use case, we actually love to hear stories. If you use tracing in production and you have an interesting story to tell, feel free to reach out. If you want to contribute, obviously we welcome all contributions, even if it's a typo in the documentation. There's a website here. We have a bi-weekly project call where we discuss sort of project direction, some issues of the day, but anyone can join and like ask questions. We also have a Gitter chat. You can find it on the website and a mail. And that's all I have. And these are the websites, and you can reach to me at GitHub or Twitter at this handle. Thank you.
Hello, everyone. My name is Eduardo Silva. I'm from the Fluentd team. I work for this company, which is called Treasure Data. And I'm going to make an introduction about what is logging and how does it works in the cloud native space. So, as part of the Fluentd team, we also have different projects, and we are going to introduce some of them on this really quick session. So talking about logging for Docker containers happens basically if you have done logging before in any kind of application, you will realize that your application just triggers some message. But when this application is running inside a Docker container, you will see that this message gets some kind of metadata, meaning where this message coming from, and also at what time this message was generated. Well, this is not new, because if you were using syslog in the past, you will see that you have a lot of that similar information along with your own message. But where this message is stored, by default or in a generic interface, if you're working with Docker containers on Kubernetes, you will realize that the message is stored in a play log file in the file system. Well, maybe you can be using journald, but normally it's like a JSON message in the file system. And how this is related with Kubernetes. So we're going to do a really quick overview about this. So in Kubernetes, I'm assuming most of you are using it right now or being introduced to it. The small granular part of Kubernetes, which is called a pod. But in general, what you deploy in Kubernetes is an application which will run inside a container. And inside this container, well, you can have many containers and one application per container. And they are grouped by in the concept which is called a pod. So if you think about logging, here, things get complex because of the region and some context for the application. And also, in one node, meaning on one virtual machine or one server, can run many pods, and many pods can have many containers. So the thing about context, origin, and things like that get more complex to realize. And in a real cluster, you don't have one node. You're not just running Minikube on, of course, in production. You have a bunch of clusters or one or many. So how do we work with logging on these kind of things? So basically, logging happens because we want to solve the main problem. It's not just about the message. It's about different concepts. If we're deploying in Kubernetes, we want to know what is the pod name associated with this message and the application. And it also comes from Docker, so maybe it has some data associated, this meaning this application is running on this Docker container, which belongs to this pod, which is running on node A, B, or C. And also there's some kind of other metadata associated with this message. For example, when you deploy a pod, you can add special labels or annotations. And at some point, you would like to extract this same information along with your own message. So in order to give a bit of context, you need to extract the container name, the pod name, the namespace which this pod is running on, the node labels and annotations. And from a log processor perspective, this can happen from the file system or journald. But all the other information comes from the Kubernetes master API server. So you can have one information from your application in one node, but the other information belongs in a separate server. So logging becomes even more complex because you need to correlate the whole information together. And that's where we introduce the logging processor for Kubernetes in general, and we have two as a project. One is Fluentd, and the other one I'm talking about now is Fluentbit. So basically, you run your cluster, you put your log processor, and the log processor aims to retrieve the information from your Kubernetes cluster, correlate metadata, and then ship out the information. You don't care about to have the information inside the log processor. You want to have the information ready for log processing, maybe in Elasticsearch, Amazon S3, or any kind of a storage solution. So log processing in Kubernetes can be done, but we need some help. And in technical terms, it happens like this. Imagine that we have some node, and this node is running 2 pods or many. The information gets stored in the file system under var log containers. And then you let your own log processor start reading the log files to gather the messages, the timestamp, and how this message was generated, maybe standard output or standard error interface. And after that, the log processor needs to go to the API server to retrieve the whole metadata. So something like simple like this, maybe you don't generate this, you just say, hey, DockerCon, then becomes a more complete message with a whole context. So this is what the problem of FluentD and FluentBit projects are trying to solve and are solving. And when we talk about FluentD, we talk about a whole ecosystem of logging tools and data processing tools for messaging from the application to perform data analysis over your storage. And FluentD is a project that as a company, we donated to the Cloud Native Computing Foundation. We are in an incubation phase. We are planning to become a graduated project. That's our goal as a project at the end of the year. And as I said, this is mostly than just one project. We also started to think how we can improve the logging ecosystem across all the, not just servers, but also clustered and all kind of environments. And some people complain that sometimes FluentD can use a lot of memory for what they need to do. So we started to think, okay, we can optimize FluentD, but there are some cases where we need special features or something better. As you know, FluentD is written in Ruby and C language, and we decided to start creating a new project under the same ecosystem based on the same experience, which is called FluentBit. And FluentBit is like a C version, I would say C version of FluentD, but with not the whole 700 plugins that we have in FluentD available, but with just maybe 40 and 50, but more focused for cloud native environments. And 1 month ago, we released the new major version, which is 0.13. And the major features of this is that you can have annotated pods. For example, the main problem with logging is that if you're going to deploy one application in Kubernetes and you want to perform data analysis, likely your information from that application is not structured. It's just one raw text message. And you need to tell the log processor somehow to process that message and create a structure, because at the end you want to query, please give me the whole statistic of the whole log messages that the status code is 200. Okay, but how do you accomplish that? So we managed to come up with a solution where we allow to the pods, in the pod definition, to say, I'm deploying this application, and we have an annotation which say, please, FluentBit or FluentD, use the Apache log parser. Please use Nginx log parser. So you don't need to redeploy FluentD or FluentBit, and you can manage that data transformation from a pod perspective. We implemented built-in metrics with JSON, we support Prometheus format, and we added enterprise connector for Azure, Kafka, and Splunk. And this is a way to add some annotated pods. It's very simple. You can set annotate this pod, FluentBit.io parser, and suggest a parser like Apache, Nginx. And also you can say, this pod, please exclude the logs from this parser and do not process anything from this. And that is mostly a use case for development and for testing. So this is an example of a YAML file. It's such simple as that. And well, this is a screenshot of the information that you can gather from the logging pipeline. It's quite important for everybody when you are monitoring your own applications, also be able to monitor your stack that is running in Kubernetes, and that includes the log processor. And with FluentD and FluentBit, you can also get the same information. We are coming up with a new version. We are going to release at the mid of July, 0.14. We're going to implement a balancing support in the Fluent bit. So if you're sending data, for example, to Elasticsearch, you can have many output nodes and balance between using round robin or any kind of strategy. And we are just implemented also Lua scripting. I'm going to talk about that. And we are planning to focus to implement a login stack driver, so you can send your logs also on Google Stack Driver service. And filtering is one kind of important thing, because one thing is data transformation, but also you would like to do data transformation in a very easy way. So we implemented a filter in which you can write your own simple Lua scripting functions and say every time that you get a record with a timestamp, just alter the data, modify very simple, and just return. So you don't need to write your own plugins in C language. You can do it on Lua. And of course, this is using Lua JIT, just-in-time compiler. It's quite fast. But if you even would like to have more performance, you can write it in C language, of course. And as from a project perspective, we are always looking for more volunteers to work on documentation, speak at meetups, events, and of course, core development. Well, that was our description about the project. We will be talking about Fluentd and FluentBit on that table, so thank you so much.
Cool, thanks. Well, hi everyone, I'm Priyanka, and I'm a contributor to the Open Tracing project. I know you've been listening to a lot of talks. I think I'm like the 7th, so great job. Great job for sticking it out. I will try my best to keep this fun and fast, because just like everyone else, I also only have 10 minutes to speak. So I'm going to do a quick overview of open tracing, which Yuri alluded to and when he presented on Jaeger. Similar to Jaeger, open tracing deals with the distributed tracing space, and Yuri did a great job explaining a bunch of concepts and reasons behind it. So it'll be a refresher course in some ways. And you can find me on Twitter always at Priyanka whenever you need to. So before we talk specifics about distributed tracing, it's important to think about the why are we all gathered here? Why are we all even talking today? And in my opinion, a big reason is that software is changing. Docker was one of the big companies that brought in the containerization movement, on top of which microservices have become much more easier to develop and deploy. So most companies, whether they're a brand new startup or an old enterprise that's been around for hundreds of years, is becoming more and more a technology company, and large old monoliths are being broken into microservices, and people are even using functions as a service to develop and ship faster to provide the best experience and product features to their end users. That's great, but the result of that is that now suddenly, instead of this one big box, you have this fragmentation of many boxes through which requests are going through the system. There's this new complexity, one, because it's different from the way people used to operate before, but also because there's an explosion of data. As I'm sure you guys are aware, adding one service and so on, like there's an exponential increase. So how many people here are developing on microservices? Almost all of you, great. So I'm sure you understand this pain better than anyone else. And how many of you are seeing a lot more data generated because you're building with services now? A few of you raised hands. Are you guys being shy? Be honest with me. So systems are distributed now, but they're also concurrent. So this is the simple and efficient thing, right? You do one thing, then another, then the next, and that's how processes go. Then as software development has become more complex, there was some concurrency added. Then we graduated to async concurrency. And at this point, we're all working in the world of distributed concurrency. So systems are distributed, and you have this crazy concurrency story going on. So how do you understand and reason about such systems? This is just 10x harder than what used to be the past. So this is where distributed tracing comes in. So in a nutshell, tracing is when you can follow the life cycle of a request from start to finish. And this diagram here is like a simple example of what that could look like. When we think about traces and distributed tracing, there are some concepts that are important to know. So this quick diagram here, you'd see like a bunch of things called spans. Span is just like a structured log. There's a start and a stop, and you can annotate it with logs or tags, whatever you might want. And there are kinds of spans, such as the parent span, which starts off things, surprise, surprise, a child that follows from it, and there's much more details in the open tracing spec about this. But the key thing to remember, if you don't remember anything else, is that a trace is a collection of spans. It's a DAG, but just think of it as a tree diagram of spans. All make up a trace to make one full transaction. So tracing offers all sorts of great things, right? You can deep dive into the anomalies and outliers and examine the exact edge case, because you'll see the full flow of the request as it goes through. This is the one chance people have to create a full system map of their very, very complex system, which no longer can sit in the head of one developer anymore. If you're doing CI/CD, you can understand why builds are slow. You can get full transaction data. So these are all amazing things, and I think many of us need those. This is an example of what a trace visualization would be. On my right, so your left, the diagram is more about like a simple architecture, and then on my left, your right, there's what a trace would look like. It's a time context visualization. So that's all awesome. Why isn't tracing ubiquitous? Well, the biggest reason is that, as Yuri pointed out, instrumentation is one of the most expensive pieces of distributed tracing. And it needs to be decoupled from vendors, which is another thing Yuri alluded to, in order to be comfortable for end users to invest in. Monkey patching is not sufficient. The software developers in working on these big systems are highly valued employees because of the knowledge that they have, and they have to decide what's the most important piece of their system to instrument and understand. Another thing is, like, people have had something specific to a library or a project, but how many people here work only in one language? Right, how many have more than one language? Right, exactly, almost everyone. You'd want to see your whole system, not just one part of it. And how many people here have open source projects in their code? Exactly. So you want some instrumentation where the projects, the code, the request as it goes through your various languages, your various open source code in there, and you get a complete picture. And that wasn't possible until open tracing without 100% manual effort. So this is where open tracing comes in, which is your ticket to omniscience. So very quickly, it's a vendor-neutral open spec for distributed tracing. By itself, open tracing is a no-op. You need things like Jaeger or Lightstep or other vendors like Instana, et cetera, to actually understand tracing information. It's built by experts in the field, such as Ben Sigelman, who was one of the creators of Dapper at Google and wrote the paper that really ushered this era in. People from Twitter, Yuri from Jaeger, all these people got together and built out the open tracing spec. Very quickly, the architecture is you have your application logic frameworks, RPC libraries, et cetera, all speak with the open tracing API. And just with a main function change, you can add in all kinds of tracers. This list here is really out of date, and you'll soon see how many vendors support the project. So lots of companies are finding it useful in production. This is just a short list. As you can see, it's like tiny. There's like startups like Samsara and like huge companies like Capital One, Staples. There's real momentum from the end user community on this. And the reason that's there is because hundreds of projects, tens of tracers, and 9 languages are supported by open tracing right now. I've tried to do a grouping here, and it's not the best. That just speaks to my poor slide making skills. But this is the momentum that's driving open tracing forward. Every day I look at the list of supported projects, and it's growing. Every day more of the software ecosystem has the open tracing footprint, and that's the most exciting thing. So that's all awesome, but what does it feel like to use open tracing in action? So I'm going to do a quick demo, and I have very little time, and I need a lot of your help to make this work. So please help me out. Get out your phones or laptop or whatever and download donut.zone. Just use your phone or laptop. I really need your help. I'm going to use my phone as well. I'm going to do donut.zone. OK, so what's going to happen here, this donut.zone side is this amazing startup I've started. It's DaaS, Donuts as a Service architecture. Move fast, bake things. So it's bootstrapped with a single donut mixer Fryer, and Topper. We just have one of each. And we've built it with an open tracing aware mutex wrapper. So like kind of baked in a little bit of slowness to show you what a problematic trace can look like. So I've cheated a little bit. Anyway, so please go to donut.zone and order as many donuts as you can, and just like don't stop until I tell you to. And this is where you can help me, because if there's not enough data, you're not going to see interesting graphs or anything like that. So this is a test to you as an audience. Click, 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 click. Lots of that. Okay, how's that going, guys? Oops. Whoops. Now I'm going to go here, as I said. Click a bunch. Hope you're doing the same. Don't be shy. Order a lot. Maybe a real donut shows up. You never know. Cool. So now I'm going to use the Lightstep tracing system to see the traces. You could use Jaeger or anything else. I'm just using this. It's like I've got this here, and it's the easiest for me. So let's see how good of a job you guys did. Very good. See this like big spike here? That's all you guys. Amazing. It's right here. I'm going to try and make this shorter so we can like really, yeah, do you see this? This is all you guys. Great work. So this spike here, as you can see, is like the P99s of the various requests that you guys sent in. And obviously, like as a developer, I want to check out what is the P99, what's the problem, let me check this out. So I'm going to click on this. Hopefully the trace is going to assemble quickly and I can actually have an interesting story to tell you. Lucky, this is good. So this is a trace view. This is what diagrammatically I'd shown you 5 seconds ago. Here, the bright yellow line going through the various parts of the tree is the critical path. Critical path is basically what's the blocker to keep things moving here, because as we discussed, there's a lot of concurrency in today's systems, and not everything is the actual blocker. So when I look at this trace, what do I see? The first thing I see is that the donut browser section, most of the time of this whole like 47-second trace is really, really egregious, I'm sure. I really hope none of your systems have 47-second transactions. Let me just say that. If you do, don't worry, we can help. So I see here that the donut browser has taken close to like 37, 38 of those. So that's like the first problem, right? That the Wi-Fi is just going a little slowly. So you know that now, and that's something you can utilize as you try to improve this situation. Then you see there's process payment. You don't know this, but I've charged you billions of dollars. And that went really fast because we can't have you figure that out. And as you see here, there's some logs annotated because this is what I had set up when I instrumented the code with open tracing. Anyway, then I go here and I see that this is taking a lot of time, the mutex acquire for donut fryer. And I see in the tags here, it says number of waiters, 175. What that tells me is that just before, the donut could go into the fryer, it was just waiting for close to, I would say, 10 seconds here behind 175 other requests. This is because you guys did a great job, and there were at least 175 requests ahead of this. And then when it comes to actually processing for the fryer, it's like a bare 50 milliseconds. So if I want to speed up this transaction, my best bet is actually to add more resources. My best bet is to add more fryers to this, as opposed to trying to improve the actual code where the donut is being fried. So that's something that you knew just looking at this trace, and you didn't have to do anything. So this is an example of a trace and like troubleshooting a latency issue. This is one view of seeing traces. As I said, there are multiple vendors you can use. But I hope this gave you a little bit of a feel for what it would be like to debug with tracing in production. Having said all that, I hope that was useful to you. These are just some demo screenshots I did just in case everything went wrong, which luckily this time it didn't, so that's always a pleasant surprise. So if you are interested in learning more, please check out our website, opentracing.io, that has a bunch of information, documentation. We hang out as a community on Gitter. Welcome everybody, all questions. There's lots of people there. And then we do some announcements on our Medium blogs. We try to release a newsletter every other month or so. God, there's so much happening with open tracing that I'm getting behind on the newsletter because it's just so hard to keep up. But that's a good problem to have. you can email us, Twitter, etc. There's like approved open tracing instrumentations that are done by the community, and we've like taken over ownership of managing them, and they're on opentracing-contrib. And there's such a wild west out there of many, many other instrumentations which are not yet in contrib but are still useful to people. Finally, about me, I'm Priyanka. You can find me on Twitter, Medium, GitHub, everywhere with the handle Pritiyanka, and feel free to reach out with any questions if I can help you get started with open tracing, if you want to use open tracing on a project you're working on, or just for any general questions around observability. With that, thank you so much, and I appreciate you guys listening.
All right, so I think we can break into groups for some birds of a feather discussions. So reminder, open tracing Jaeger on that side, Istio, Kubernetes contributor experience, Spiffy, CSI, and Fluentd on the other side. So please let's give a last round of applause for all the speakers this afternoon.